everybody, welcome to lecture 26 on climate. So this week we are going to be talking about climate change, global warming, pollution, all that fun stuff. But before we do that, we need to look at climate and how it forms and how it controls basically our entire planet. There we go. Before we talk about climate, we have to talk about our atmosphere. So currently, Earth has a very well-developed atmosphere, and it's comprised of a mixture of gases called air. And air is what we breathe. It's also what keeps our planet warm. At this moment, it's keeping our planet a little bit too warm than we would like, right? But it's this very important envelope, or another way to think about it is a blanket around our Earth, and it protects us from UV rays. It gives us nice air to breathe, and let me pull this over. And it makes it a habitable and livable planet for us, right? And you can see in this diagram that it took quite a while for our atmosphere to develop. Billions of years ago, Earth was not a livable place. It was very harsh, hell-like type of environment. It took a very, very, very long time, thanks in large part to our stromatolites. So if you watched that video on Making North America, you learned that our stromatolites gave the atmosphere all of this nice oxygen that we currently did not have. Excuse me, I'm just going to put a timer on because I don't want to take up too much time. Okay, start. Cool. All right, there you go. Okay, so our atmosphere formed over billions of years, and now it's comfy, it's good, but it's currently, in the last century to half a century, has not been so great. So we're going to get to that eventually. But first, let's talk about our atmosphere. So when I go through these slides, I'm going to go quickly through because I don't want to just read from the slides. You can all do that yourselves, but I will stop making some points here and there. So that'll be the vibe for these next few lectures. Okay, so here's a couple of diagrams showing you Earth's early atmosphere versus Earth's modern atmosphere. So you can see the different types of chemicals that are in the atmosphere. Nitric oxide, carbon monoxide. Now we have carbon dioxide. We have some methane, which is CH4. We have some oxygen. We have some H2O, some water vapor in the air. Okay, so that's the difference between early Earth versus modern Earth. And you can see how long that took in Earth's history before we got our atmosphere, which is comfortable for us today. And here's a nice website that you can go on and visit. Okay, so what is our composition of the atmosphere, right? We talked about nitrogen, oxygen, and then we have a couple of other gases, but it's mostly nitrogen and oxygen. Okay, other gases include argon, carbon dioxide, methane, sulfur dioxide, ozone, radon, and aerosols. Okay, and so if you notice here, about 1%, a little bit less than 1%, are other gases. And if you look at other gases, you see argon, carbon dioxide, methane, sulfur dioxide, and ozone. Okay, and so what we're going to talk about later is that this little sliver, this 1% of our other gases in our atmosphere, is actually causing a huge problem with global warming. So when we emit carbon dioxide, which is only a really small percentage of what our atmosphere composition is, along with methane and some other unfriendly gases, it can cause some really catastrophic effects for our planet. Okay, so that's just something to keep in mind. Okay, whereas nitrogen and oxygen are the predominant gases, and only a little tiny percentage of that is other gases, which are actually pretty problematic. And this diagram is neat here because it shows you how the concentration of oxygen in the atmosphere has changed in the past 700 million years. Okay, and you can see a pretty large spike here about 300 million years ago. There we go. Okay, so this is a nice diagram showing you the different layers of our atmosphere. Okay, so the difference between where we live, breathe, sleep, eat, here down. Let me just move this over. There we go. Okay, in the lowest layer of our atmosphere, so the troposphere, and then we have the top of Mount Everest where airplanes fly, in our stratosphere, and this is where the ozone layer resides and protect us. So you can see that if you are in an airplane, you can see our stratosphere, mesosphere, and thermosphere, and these are the top layers of our atmosphere. Okay, and so this is the mesosphere is where the air is really cold, and the thermosphere is where individual molecules are very hot. So you can see the different temperature differences as you rise through the atmosphere and you rise through the different layers of the atmosphere. Okay, so the atmosphere doesn't exactly get super cold as you ascend, right? There are some temperature differences throughout the layers. Okay, but one thing that does definitely increase and decrease depending on altitude is pressure. Okay, so this is a nice handy diagram for that. Okay, again with the temperature and atmospheric layers, so I won't get too into this. Okay, so our atmosphere, this is no good place to put me. Okay, so our atmosphere really regulates climate on a global scale. Okay, so our atmospheric circulation is a huge dictator into what types of climates we have and where those climates are located on our planet. Okay, so this thing called atmospheric circulation cells create the general climate of a region. Okay, so the solar energy on Earth is not equally distributed, right? And so the largest amount of solar energy is located close to the equator here, right? Whereas the polar regions don't get as much solar bathing, right? And this has something to do with atmospheric circulation. Okay, so I'm gonna go to the next slide because it's better. Okay, so in this diagram here, you see atmospheric circulation as if Earth did not rotate. Okay, so similar to how we have convection in our mantle, right? We have warm things are more buoyant and less dense. They like to rise, right? Well, the same type of convection happens in our atmosphere. Our warm things, our warm air likes to rise because they're buoyant, they're less dense, they want to float up, right? The cold stuff wants to sink, right? So if our Earth did not rotate, we would have two really simple atmospheric circulation cells, which is shown in this picture here, right? We have warm air rising, it's more buoyant, and then as it cools, it sinks, right? And you get this nice circulation cell back and forth, and you would get this along the equators. So there would be two big circulation cells. But because we have atmospheric circulation, we have this funky thing called the Coriolis effect. And it's when pressure moves things in a lateral way, causing a kind of circular type of pattern, right? And so this is why we have a couple of different convection cells. So the best way that I can explain the Coriolis effect is through this really cool video that's here. Okay, I'm not going to play it, but watch this because it does a really, really good job explaining the Coriolis effect. Okay, so because of the Coriolis effect, we have 3 circulation cells, okay, instead of 2. And so you can see that we have 2 right at the equator here, and then we have 2 more in our polar regions and right below the equator. So about that 30-degree latitude line is where we get these different types of circulation cells. Okay, and that has everything to do with the Coriolis effect, which this video does a much better job, and it's cool. They do a nice experiment with the Coriolis effect, so it's a nice, really cool visual, so please watch that. Okay, so this atmospheric circulation in the Coriolis effect, where different cells are generated because of this pressure being pulled from high pressures to low pressures, right? We get these convection cells. So you can see we have 3 on one side of the equator and 3 on the other side of the equator, right? And so the same type of deal is happening on the other side of the planet, right? We have these nice 3 convection cells. Okay, and so you can follow this global atmospheric circulation diagram to show you how the warm air rises and then the cool air sinks, and how that is generated based on these high and low pressures that are on our planet. Okay, and so I also like this diagram here because it shows the different types of climates that you'll expect to find based on these 3 circulation cells. Okay, so you can see towards the equator, where we have our biggest solar energy located, we have hot deserts, we have deciduous forests, we have tropical rainforests, etc. And then if you look towards the center convection cell, you see this hot and dry region, right? We've gone from really hot and moist, there's some rain, precipitation going on, to right at the edges, we have this really hot and dry region. Okay, and then towards the top, we start to get these temperate forests. So we have our evergreens, our coniferous, our temperate grasslands, and then we have our cold deserts. So our polar caps are actually deserts, but they are cold deserts. Okay, keep on moving. Okay, our climate is also impacted by the Earth's tilt. Okay, so we went over this way back in the day. Earth's tilt is causing of the seasons. Okay, so I'm not going to get too into that because we should already know. And here's a nice picture of the different seasons, January versus July. Okay, so we have this atmospheric circulation. So hopefully you watch that video and it makes a lot more sense. And this is what's dictating the climate, right? We have these big atmospheric circulation cells that are generating these different types of patterns based on the latitude of the Earth, right? And that changes with latitude. So you can get really different climates on the equator versus the polar cap regions, okay? But what is weather, and what is the difference between weather and climate? Okay, so weather is really a local scale conditions of temperature and pressure. So T and P is temperature and pressure. Humidity, precipitation, cloud cover, wind speed. This is all local, very localized events, right? So you can think rain, thunderstorms, tornadoes, hurricanes. This is all weather, right? And weather conditions can vary dramatically. And weather is really, really difficult to predict also. So the difference between weather and climate is that weather is really variable based on the specific region. So it's really local and varies depending on city, depending on state, etc. It's also really hard to predict. So it's very difficult to predict timing. Whereas climate is easier to predict because it's over longer scales of time, right? So these weather patterns influence climate, but they are really the culmination of multiple years, over 30 years of weather averages that can make up the climate. So climate is you're able to predict climate, you're able to understand it on longer term scales because it is basically weather averaged out over very many years. Okay, and so what are the culprits behind weather and what causes it and what drives it? Well, it's really atmosphere, right? It's our air masses. We have different temperatures and different pressure air masses, and they are being circulated over the globe. These air masses are cold and they're warm, right? And they flow over the earth at different temperatures and pressures. And this causes our weather, right? So everything in our atmosphere causes climate, and it also causes weather. So our atmosphere is a very important layer of our earth. Okay, and so here's some diagrams on cold and warm fronts and how these form, right? And you can just picture these masses of air flowing over the earth and colliding with one another. Okay, and this is what causes our different types of weather events, our storms, our thunderstorms. It's all really comes down to temperature and pressure. Okay, I'm not going to go over these. These are some storm events. Okay, clouds and precipitation. Again, we're still talking about weather and different weather events, right? So clouds form when water vapor and saturated air condenses, okay? And cloud forming saturation occurs when air is lifted and cooled. So on this diagram here, we have convective lifting. Okay, and so this is what happens when you have air masses come in contact with different types of bodies, whether that be land, ocean, or mountains. So this particular one is called localized convective lifting. Okay, and so this is what happens on warm summer days where you have a pocket of air warmed more than the surrounding air. So a lot of times this happens when you have a really warm body of land, like say a parking lot, or something that's being baked on a warm sunny day, maybe somewhere in Texas or down south. Let me see. Right, there we go. So you have a pocket of warm, low density air rises, right? And this is pulled from the warm body of land where it has this warm, low, dense air, right? And this creates a rising air effect, right? You get this convective lifting, and the air is heated by the ground. The opposite happens when you have convergence lifting, right? So this is when the air comes in contact with nothing. So the winds merge and the air has nowhere to go up. So you have these clouds forming, one by this low density air coming in contact with some warm land. So you can think somewhere down south, or you have this convergence lifting of clouds when they have nowhere else to go. So this is why we have these storm events happening over the ocean and why we have them happening, let's say somewhere down south, right? We have this convective lifting happening because of air coming in contact with various things. Now, something that's different from these two is called orographic lift. Okay, and so this is a cool one. I like talking about orographic lift. And it's when these air masses come in contact with topography. So let's say steep mountains, a nice volcanic chain, right? And these are usually on coastal boundaries. So think northwest corner of America or South America, you have these coastal mountain ranges, right? And you get some moist air rising from the ocean, right? And it's going to orographically lift because the air is rising up over the mountain. Okay, but as it descends, all of the moist air is trapped by the mountain on the ocean side, and as it descends, all of that moisture is lost because it's trapped, right? And you have all this dry air descending. So if you ever go to a mountainous region, such as the northwest corner, it's a great example. You have this thing called a rain shadow, and it's where you have these mountains trapping all of this moist air on the ocean side and releasing all of this dry, basically lacking of any type of moisture descending on the leeward side. So a good example is, again, the northwest corner. Oregon, this is a satellite image of Oregon, and you can see that this is all a mountainous range here. So you have the Cascade Range, Mount Hood, which is a volcano, and this is all mountain here. And if we were to extend this map, this would be the ocean here. So as the air is coming in contact with these mountains, it's trapping all of that moist air coming off of the ocean. But on the other side of the mountains, you see all of this dry desert. So if you ever go to Oregon or the northwest corner, there are actually desert regions that you can visit just right over the mountain, because this orographic rain shadow is trapping all of the moisture on this ocean side. And it's very, very, very dry on the other side of the mountain. So it's cool. So again, here's Washington. You can see this really dry desert region here, and all this really moist, lush green region on the other side. Okay, we also have clouds and precipitation. I'm going to just check my time, make sure. Okay, keep it moving. Okay, we have clouds forming. Again, these are all just relationships with air temperature and pressure and moisture. Storms, thunderstorms, lightning. Again, these are all different weather patterns. Tornadoes. Okay, this is how a tornado forms. Here is a nice tornado map showing where most of the tornadoes are going to form. And if you notice here in the northeast region of Connecticut, Massachusetts, you see a 1, right? So if you've all been around Massachusetts or the Northeast enough, you know that every once in a while we do get a tornado in the summer. Sometimes they are pretty damaging, not as damaging as in this Tornado Alley region here. From Texas to Indiana. Again, these are where these polar air masses collide with warm, moisture-laden air, right? So you're getting this warm air colliding with this cold air, right? So that's what a lot of these weather patterns are caused by, right? Just all of this air mixing and mashing with each other and creating unstable air, which is what our storms, our tornadoes, our clouds, our rain, that's all unstable air, right? Because it's mixing with warm and cold and different types of pressures. Okay, but this northeast region also gets some tornadoes, so that's something cool to remember. Okay, hurricanes also. Cold, dry air is pulled down into the eye to create a calm, and spiral arms mark rotating air as it's pulled inward, right? So it's all spiraling, warm, dry air mixing with warm ocean water and warm water vapor. This is a pretty crazy picture of Hurricane Hugo in 1989, which was a terrible, devastating hurricane. Okay, I'm not going to read through these, but you can do them on your own time. Hurricanes, extremely devastating. Okay, back to climate. Okay, so all of these things that we just talked about, hurricanes, storms, etc., this is all different weather patterns, right? But the word climate refers to persistent weather. So again, that's 30 years or plus of regional trends. Okay, so what are these trends? These are temperature, pressure, humidity, precipitation, wind conditions, and storms, right? So this is the culmination of weather for 30 years or more, right? So climate, you're summing all of these different types of weather patterns together. Okay, and what is it controlled by? It's controlled by latitude and altitude. So again, remember the air changes as you ascend. Okay, so as you get ascend in the air, did you get different temperatures and different pressures? Okay, and so that varies with latitude. So remember, latitude are horizontal bars across the earth. Longitude are these vertical bars across the earth, right, creating a grid pattern, right? So latitude is what runs across our equator, right? So that's latitude. Okay, so proximity to water. So water affects the different types of climate that you'll have on Earth. Ocean currents, mountain ranges, and pressure zones. Okay, so you'll get different types of climate depending on how high your mountain ranges are. So we're going to look at a couple of these, and here's a nice summary of all the different types of climates that we have on Earth, right? And of course, these affect the different types of vegetation that can grow. Okay, where's that chart that I wanted to show you? The next video is talking about climate variability, and it's summarizing El Nino and La Nina. It does a really nice job. So that's another video that you have that you can watch on your own time. Okay, so back to how climate conditions on land are affected. Okay, so what are the effects of climate and how is it controlled? Okay, so we talked about latitude, land cover, atmospheric circulation is what we talked about in the beginning of this slide, ocean circulation, topography, and proximity to ocean. Okay, so insolation again is all about latitude. Okay, so remember the rotation of the Earth is on its axis, and the angle of incidence, which is this insolation of the sun's rays, is influenced by this axis of the Earth. Okay, so the rotation of Earth's axis. Okay, so you can see here that you have this solar radiation diagram here. All of these yellows and oranges are really centralized right around the equator, okay, right through the center of the Earth. And then we have lower amounts of solar radiation in our atmosphere in the polar regions in north and south of our planet. Okay, so again, this all has to do with latitude and Earth's axis rotation. Okay, here's some more diagrams showing you that. Okay, so climate is also influenced by ocean circulations. Okay, so we have our ocean circulations are, again, similar to our convection cells, right? So we have warm air rising and our cool air sinking. So the same thing is happening in our ocean currents, right? We have a warm surface flow flowing through this type of pattern on the surface. So this is where we get our warm surface waters from. We have this ocean current where we have our warm waters floating, they're more buoyant, and they're going to create this current in the superficial type of depth, right? But as these waters cool, they sink, right? So cool things like to sink, and as they sink, they start this secondary flow pattern, right? And so it kind of makes this a little infinity type of pattern across our planet, right? So we have our warm rising, our cool sinking. Okay. Again, the effect of atmospheric circulation, right? You see these bands forming around 30 degrees north and 30 degrees south latitude, right? Our equator, which is this 0 degrees, has a specific type of atmospheric circulation, whereas our 30 degrees north and south, you can see these white and green types of colors, right? And then our polar regions are also completely different based on atmospheric circulation. Okay, we talked about that. Okay, and then topography. So again, our climate is impacted by topography, so our big mountain chains. So this is a global annual mean temperature diagram, and you can see, again, we have our hotter regions right along the equator. But one anomaly that you can see in South America specifically is this band of green, or this band of slightly cooler temperatures, right? So we have reds, yellows being pretty hot. We have greens and blues being pretty cold, right? But you see that even though this mountain chain is close to the equator, it's pretty green. It's a lot lower of a temperature than the surrounding area, right? And that's because of the topography. There's these high mountain chains that are causing this climate variability right along the equator where it should be hot, but there's these really tall mountains, so it's cold. You can also see that really well in the Himalayas, which is this region here, right? The surrounding area is pretty warm, but right at the border, you see this huge temperature contrast where it's all these blues and greens, right? And those are the Himalayan mountains because they're our tallest mountain system in the world, right? So it's going to impact the climate in that region, right? So topography is going to affect climate. It's also going to affect where you get glacial and sea ice. Okay, so here's a polar ice cap showing you the differences between the 1980s and the 2010s, and we're going to talk about climate change in the next lecture. So stay tuned for that. Right, and I think this is our last slide, and this shows you global precipitation. So where we see more rain events than others, right? And again, these are all have to do with our atmospheric circulation. It all goes back to our atmosphere. All of these convection cells are operating differently depending on where they are latitudinally on our globe, right? So this is all connected to our atmosphere. So climate, weather, ocean currents, these all have to do with our atmosphere. The only things that are kind of different with our climate is our topography. So that can make things kind of funky. And with that, that's the end. We'll stop. I will see you next lecture 27.